Hello students, in this video we are going to discuss question number 51 to 60 from gaseous state from problems in physical chemistry for JEE mains and advanced by Narendra Avasthi. In question number 51, the intercept on axis y and slope of the curve plotted between P by T versus T. So as we know that for ideal gas, the P by T versus T plot will look like this. P by T versus T plot will look like this. Okay, as now we can see that the slope of this graph is 0. Okay, so we have to find the slope for the graph also. So here we have to calculate the intercept, value of the intercept and slope of the graph. Okay, so PV equal to nRT or P by T equal to nR by V. According to the problem, we have 10 moles of ideal gas. So 10 multiplied by 0.0821, that is value of R, divided by volume, and the volume is 8.21. Okay, so finally P by T value will comes out 0.1. Okay, so intercept value is 0.1, so we have to find intercept and slope. So intercept is 0.1 and slope is 0. So according to this, option B will be the correct option. In question number 52, the helium atom at 300 Kelvin is released from the surface of the earth to travel upward, assuming that it undergoes no collision with other molecules. How high will it be before coming to the rest? Okay, so the energy, potential energy mgh is equal to 3 by 2 kT here. K is Boltzmann constant and T is temperature of the system. Now the height can be calculated as 3 by 2 kT divided by mg. So 3 by 2, value of Boltzmann constant is 1.38 into 10 to the power minus 23 multiplied by temperature 300 divided by mass of helium atom, 1 helium atom. So 4 divided by 6.023 into 10 to the power 23. So divided by Avogadro's number will give you the mass of single atom, multiplied by G 9.31. So if you solve this, the height will become 9.53 into 10 to the power 4 meter. So option D will be the correct option. In question number 53, the density of gas A is twice that of B. At the same temperature, the molecular weight of gas B is twice that of A. The ratio of the pressure of gas A and gas B we have to calculate. As we know that D equal to Pm by RT, and for this dA by dV can be written as PA by PB multiplied by MA by MB, because all the other things are constant. Now according to the problem, dA by dB is 2, PA by PB we have to calculate, and MA by MB is half. So from this we can calculate PA by PB, which is 4 by 1 or 4:1. So the ratio of the pressure of the gas A and gas B will be 4:1, and option C will be the correct option. In question number 54, we have two balloons, and in the case of balloons, the pressure is constant. Okay, pressure is constant because they are stretchable. Okay, so here we can write for balloon problems P1 V1 by N1 T1 equal to P2 V2 by N2 T2, where pressure is equal, so P1 equal to P2. It is a leak proof balloon, that's why N1 and N2 they are also same. So working formula for any type of balloon question is V1 by T1 equal to V2 by T2. Now we have to calculate the temperature after which it can burst for outer and for inner separately. So for inner balloon, 600 volume initially, 300 temperature initially, 800 the maximum volume it can achieve, and T is the temperature after which it can burst. So if you calculate, it will become 400 Kelvin. And for outer balloon we can calculate by same process, initially it is 1500, initial temperature is 300, finally it can have 1800, and the final temperature after which it can burst, that is 360 Kelvin. So if you increase the temperature from 300 Kelvin, because the initial temperature is 300 Kelvin, ml is not the correct thing, 300 Kelvin. So initially if we start with 300 Kelvin, we will touch 360 first, then we can go for 400. So between inner and outer balloon will burst first. So option B will be the correct option. In question number 55, an open flask contain air is heated from 300 Kelvin to 500 Kelvin. What percentage of air will be escaped to the atmosphere if pressure is keeping constant? So in this question, we can simply use P1 V1 by T1 equal to P2 V2 by T2. So initial volume is V. Finally, initial temperature is T1 and pressure is keeping constant. So we can cancel the pressure. We are calculating final value V2 when the temperature is 500 Kelvin. Okay, so from this we can calculate V2, which is 5 by 3 of its initial volume. So it is a change in volume. So finally it is 5 by 3 volume minus initially it is 2. So the change in volume is 2/3. So now we have to calculate the percentage. So change divided by V2 multiplied by 100 will give you the percentage. So 2B by 3 divided by 5V by 3 multiplied by 100, and from this we can calculate it is going to be 40%. Okay, so option B will be the correct option. In question 56, the value of universal gas constant R depends on. This question is not correct because the options are not correct, because that if we see PV equal to nRT, then R equal to PV by RT, sorry, PV by NT. So the value of R, it depends on pressure, volume, number of mole and temperature, all of them. So temperature of the gas, number of mole, volume, all of them are correct. Units of volume and pressure, see, value of universal gas constant it not depends on the unit of volume of pressure. So we can say that it not depends on option D. Okay, but it depends on A, B, C, all of them. So there is some problem in this question, so we can skip this question. Question number 57, a manometer attached to the flask contains the ammonia gas here, and after some sparking we can see that there will be some dissociation in the ammonia gas. Here we have constant volume and temperature is also constant, so PV equal to nRT. If we have constant volume and constant temperature, we can see that pressure is directly proportional to mole. So if we have initially ammonia gas, after dissociation it is giving this and this. So initially the pressure is 1 atm according to the question, because there is no difference in the mercury level. So the atmospheric pressure equal to the ammonia pressure, and after dissociating, if we are taking a random value of 2x, so it will give x and it will give 3x. So final pressure will be 1 minus 2x plus x plus 3x, which is nothing but 1 plus 2x. Now this 2x extra pressure is the cause of the difference between the mercury level, that is 6 cm. So 2x is the pressure difference, which is the cause of difference in mercury level, that is 6 cm. So value of x is 3 cm. Okay, now we have to calculate the partial pressure, that is 3x. So according to this problem, the partial pressure of hydrogen is nothing but 3x, that is 9 cm of mercury. So for this question, option A will be the correct option. In question number 58, we can see that atmospheric pressure is equal to pressure of the gas plus pressure of the liquid, here it is water, of 8 cm, and aqueous tension. Aqueous tension is basically surface tension. It will act downwards. Okay, so here we can apply H1 rho 1, H2 rho 2 to convert this to atmospheric pressure. So here we have height of H and it is water, so density is 1. We have to convert it in mercury. Okay, so we are using H2 as mercury, or H of Hg of mercury, and density is given by 13.6. so the height of mercury column will be H by 13.6. so here we can substitute PL by H by 13.6. now P of ATM, atmospheric pressure, can be written as pressure of the gas plus H by 13.6 plus aqueous tension, and from this we can see that pressure of the gas will be pressure of the ATM minus aqueous tension minus 13 H by 13.6. and for question number 58 the correct option is going to be option A. In question number 59, a bubble of gas released at bottom of the lake increases to 4 times of its original volume when it is reaches at the surface. Assuming that atmospheric pressure is equivalent to pressure of 10 meter water column, what is the depth of the lake? So we can apply P1 V1 equal to P2 V2 here. Okay, so V1 is V and V2 is 4V according to the problem, and P2 is nothing but 1 atmospheric pressure. So here if we apply this, we have to calculate P1, and V1 is given by V, P2 is 1 atmospheric pressure, and volume V2 is 4V. so if we cancel this one, the initial pressure is going to be 4 atm. But for the initial pressure we have two things, that is atmospheric pressure and pressure of the water column, and atmospheric pressure is 1 atm. So pressure of the water column will become 4 minus 1, that is 3 atm, and 1 atmospheric pressure indicates 10 meter of water column height. So 3 atmospheric pressure indicates 30 meter of water column height. So depth of the lake should be 30 meter, that is option C will be the correct option. In question number 60, calculate the number of mole of gas present in the container of volume 10 liter at 300 Kelvin if the manometer containing glycerin showing 5 meter difference in the level showing in the diagram. Okay, so first of all we have to convert 5 meter of glycerin into mercury level. Okay, so that's why we are using H1 rho 1 equal to H2 rho 2 thing. Here H1 is 5 meter, that is 500 centimeter, and density of glycerin is given as 2.72. height of the mercury level you have to calculate. We can write it like H of Hg and 13.6, and the mercury level or height of the mercury level is going to be 500 multiplied by 2.72 divided by 13.6. okay, centimeter of Hg, but we want to convert it in atm, so we can divide this by 76 centimeter of mercury, and finally it will become 1.315 atm. okay, so we are converting it into atm because we want this pressure to be used in PV equal to nRT, and N number of mole can be calculated as PV by RT. So what is the pressure? Now the pressure of the mercury level is 1.315 atm, but we have another pressure, that is atmospheric pressure, because this is an open container. So total pressure is 2.315 atm. So 2.315 multiplied by volume of the container, which is given as 10 liter, divided by 0.0821 multiplied by temperature of the system, that is 300, and if you solve this, you will get 0.939 moles, which is near to 0.94 moles. So according to this, option A will be the correct option. Thank you for watching.